Dear students, in this paper of Organic Chemistry Part 3, we shall be dealing with the reaction mechanism in continuation, that is, it is the reaction mechanism 2. And under this we shall be studying about the free radical reactions, where we will go into detail the structures, the substitution mechanism at the aromatic substrate, and then we shall be studying about some named reactions as well as other examples which take the radical reaction pathway. After this, we shall be focusing our study in this paper on the addition to the carbon-carbon multiple bonds. How the mechanistic and the stereochemical aspects are important in the addition reactions which involves electrophiles, nucleophiles and the free radicals we shall be discussing in detail. And we shall be studying about the regio and the chemoselectivity, the various orientation and reactivity. We shall be also studying about the addition on the cyclopropane ring, which acts like a multiple bond because of the strain, and some named reaction under this. After this, we shall be moving to the addition to the carbon hetero multiple bonds like carbon oxygen, carbon nitrogen, double triple bonds, how the reactions takes place in these, that we will be studying. And there will be a focus on the metal hydride reduction of saturated as well as unsaturated carbonyl compounds, acids, esters and nitrile. We shall also study some named reactions, and that will be like aldol, novinagel, Claisen, Mannich, benzoin, Parkane and Staub reaction. After the addition reactions, our focus will be on the elimination reactions. We shall study how the E2, E1, even CB mechanisms they take place, what is the orientation of the double bond, the reactivity effects of substrate structures, the attacking base, the leaving group and the medium, how these affects the elimination, that all we will study in detail. And we shall also see how the pyrolytic elimination take place. After elimination, our focus of study shall be on pericyclic reactions. Here you shall be acquainted with what are the frontier orbitals of ethylene, or the molecular orbital symmetry, the classification of various pericyclic reactions, and then the Woodman-Hoffman rules, the correlation diagrams, the FMO and the PMO approach, all that we will be studying in detail. We shall be focusing further on the cycloadditions, the electrocyclic reactions which can be 4n, 4n plus 2, the allyl systems, how the con-rotatory and disrotatory motion will have effect, all that we will be studying in detail. And here also we shall study about some named reactions which are Claisen, Cope, Azacope reactions, and also we shall study fluxional tautomerism. Let us begin with the first module, and the first module will deal with the free radicals, and in this module and subsequent modules we shall be studying about free radicals. Now in this particular module we shall be going into the details of the structure and stability of free radicals. After studying this module, you shall be able to know about the free radical structure, learn how the different type of free radicals can be generated. You shall be also able to learn about the factors contributing to the stabilization of the generated radicals and analyze the factors affecting radical generation. You are already aware that the fission of a covalent bond by homolytic cleavage, that is equal cleavage, in which both the atom possess unpaired electrons due to the symmetrical rupture of the bond. And as you can see here, the bond between X and Y, it gets homolytically cleaved, and you will be getting X with unpaired electron and Y with unpaired electron. And these fragments, which are although neutral species but have unpaired electron in them, they are called as free radicals. So we can thus define a free radical as an atom or a group of atoms with an unpaired electron. Free radical intermediates are often involved in reactions carried out at high temperature or under the influence of light. Even at room temperature, many reactions proceed by a free radical mechanism, particularly in non-polar solvents and in the presence of substances known to produce radicals such as peroxides. Most common radicals are extremely reactive species and they are difficult to isolate. Such radicals are referred to as short-lived radicals in contrast to the stable free radicals which are not so reactive and exist in equilibrium with the normal compounds. And there are a number of compounds where homolysis is particularly important to chemists like dibenzoyl peroxide and AIBN, which is azoisobutylonitrile, which are often used in important synthetic reactions. If we talk about another commercial use, it involves the administration of tetraethyl lead in petrol, which has now been discontinued. The radicals generated from it react with other radical species involved in the pre-ignition of petrol vapor in the internal combustion engines and thus prevents the phenomena of knocking. Similarly, there are many reactions which are taking via the route of free radicals as intermediates. So, let us go into detail about what are free radicals and let us begin with knowing what is the structure of free radicals. Let us try to know the structure of these free radicals. In the case of simplest organic free radical species, we can have methyl radical. If you look at the methyl radical, the radical center, that is the carbon here, is trivalent and it is trigonally hybridized. You can say it is the sp2 hybridized carbon and which is coplanar with the 3 hydrogen atoms, as you can see in this structure. The unpaired, which is the odd electron, note that it occupies a 2p carbon atomic orbital and it has been arbitrarily designated here as 2pz. This singly occupied orbital is often abbreviated as the SOMO, that is singly occupied molecular orbital. SOMO or SOMO is of special importance to the free radical chemistry. And note that in this structure, the 3 hydrogens and the carbon are in a trigonal fashion in a plane and the p orbital is perpendicular to this plane and this p orbital has this unpaired electron. The odd electron in free radicals can have either alpha or beta spin. Hence, there are 2 spin states for free radicals which are energetically distinguishable in the presence of a magnetic field, but in the absence of such an external field, they are isoenergetic. Free radicals are termed as spin doublets because of the existence of these 2 discrete states. And you will see later when you study the NMR, there will be impact on that how you can really notice the free radicals in an NMR spectra. Now, let us study about how these free radicals can be generated, that is the generation of free radicals. You are already familiar with the mechanism of radical chain reactions, that is halogenation of alkenes. If you recall, in this reaction, chlorine free radicals are generated by either thermal or photochemical homolytic bond cleavage. As you can see here, in the case of chlorination of methane, the reaction is generally carried out at high temperature around 250 to 300 degrees centigrade, and under these conditions the thermal homolytic cleavage of the Cl-Cl covalent bond, as you can see, will give rise to 2 chlorine free radicals. Now, this range of high temperature is required in order to dissociate the chlorine molecule fast enough to effectively initiate the chain mechanism, and this is because the Cl-Cl bond has the bond association energy of having a high value of 58 kilocalories per mole. For most of the organic reactions involving radical chemistry in the laboratory, radical formation is initiated at temperature below 100 degrees centigrade by adding a few percent of a substrate which is called as an initiator, and this will have a relatively weak bond. For example, peroxides which have a weak oxygen-oxygen bond are perhaps the most common choice. In the case of bromination, since the molecular bromine absorbs UV light, homolytic dissociation to bromine atoms can be accomplished even at room temperature or even below by the photochemical means, that is by irradiation. First of all, let us see how the thermal reactions can be used to prepare the free radicals. Historically, the first work to demonstrate the formation and existence of free radicals was that of Penneth and Hofche in 1929 to 31, and their procedure, often referred to as Penneth technique, consisted in passing a stream of nitrogen and the vapor of tetramethyl lead through a quart tube. The pressure in the quart tube is held at about 2 mm by the action of a vacuum pump, as you can see in this visual. So, under these circumstances, the tetramethyl lead then decomposes to form lead and methyl radical, as you can see here, and further the methyl radicals produced as a result of heating at point B, they react with the mirror at point A to regenerate the volatile tetramethyl lead, and in the absence of lead mirror, the methyl radicals further combine and they can give you ethane. Similarly, there are many other examples where thermal generation of free radicals can be done. For example, those compounds which possess an intrinsically weak bond like dialkyl peroxides. These dialkyl peroxides, on heating, they produce alkyl free radicals, as you can see in this example. Similarly, those compounds which on fragmentation they form strongly bonded products. For example, AIBN, that is azo bis isobutyronitril, having this structure, on heating releases the nitrogen and it will generate the free radical. As you can notice, the central C is having this unpaired electron which is further joined to 2 methyls and nitrile group. After the thermal generation, let us look at photochemical generation. As the name suggests here, light leads to the generation of free radicals via the fragmentation of a compound. This can be achieved if the wavelength of the light corresponds to both to an energy greater than that of the bond to be cleaved and to an electronic excitation of the molecule concerned. This procedure is suitable for the formation of alkoxy radicals from alkyl nitrile or hypochlorites. Very frequently, photochemical dissociation is preferred to thermolysis, as in case of thermolysis it will many other byproducts, but in photochemical it is more selective reaction. For example, the phenyl radical is one of the most important species in combustion process. While it can be generated by photolysis of iodobenzene or dibenzyl peroxide, the FVP, that is the flash vacuum pyrolysis of trans-azobenzene, followed by trapping of the fragments in solid argon, provides a cleaner synthesis of the phenyl radical thus produced. Reaction of the matrix isolated phenyl radical with oxygen yields the phenyl peroxy radical in a diffusion controlled process. Irradiation of phenyl peroxy radical with visible light leads to its rearrangement, as you can see here, into 2-oxy-phenoxy radical, while the phenoxy radical is not formed under the conditions of metric isolation spectroscopy. Extended photolysis of oxy-phenoxy radical finally yields the ketene radical, and if a matrix containing phenyl radical and water is annealed, initially a weak complex phenyl radical water is formed which yields a benzene hydroxy radical complex upon photochemical excitation, and you can notice all these steps as shown in this particular visual. After the photochemical, let us move to redox reaction. Many of the redox reactions in between they give you free radicals. One electron oxidation reduction reactions are very often employed to produce radicals. Covalent bonds here may be broken by electron transfer process, either by accepting an electron from a donor or by donating an electron to an acceptor. Now, one such reaction that has considerable synthetic importance and that you are already aware in your earlier classes is the Coles electrolysis of the salts of organic acids. That is, you take the silver salt of carboxylic acid and that on heating will give you the loss of one electron from the RCO minus, you get RCO dot, and further out of this the carbon dioxide gets removed and there is a generation of R dot, which is the alkyl free radical. Further, these alkyl free radicals combine to give you alkane as the product of the Kolb's reaction. Another well known example is that of the Fenton's reagent produced by the reaction of hydrogen peroxide with ferrous ions. As you can see here, Fe2 plus with H2O2, there will be generation of Fe3 plus, OH minus and OH dot. The generated hydroxyl radicals can then be used as oxidizing agents to oxidize the organic substances. As you can see here, it can oxidize benzene and it can give you phenol as a product. Let us now move to radical stabilization after having known the various methods of generation of free radicals and their structures. The factors that affect the free radical stability, with them one by one. Like carbocations, the free radicals are electron deficient species. There are 7 electrons in the octet of the carbon, so it is an electron deficient species. It is useful to know that the factors which affect the stability of free radicals are the same which influence the stability of carbocations, and they can be stabilized through the donation of electron density by neighbors, and for this reason the radical stability increases in the order of methyl being least stable, primary will be more stable, secondary will be even more stable and tertiary being most stable. So, radicals are also stabilized by adjacent atoms which have the lone pairs like oxygen and nitrogen, where they can go into resonance for stabilization. A second important factor which stabilizes the free radicals is delocalization. That is, if the radical can be spread out over 2 or more atoms. So, one is where you have the alkyl group, predominantly it will be their inductive and the hyperconjugative effect for stability, just like the carbocations, and the other important factor is the delocalization, where you have the adjacent atoms which can help in the delocalization. So, a more familiar way of saying this is that free radicals are stabilized by resonance. So, as you can see in the visual here, that out of a normal primary and a allyl, obviously the allyl free radical will be more stable because they can be delocalized. Similarly, if you look at this cyclohexyl with CH2 dot as the free radical, which is aliphatic, but if you make the corresponding benzyl radical, then obviously the benzyl radical will be more stable. As electron deficient species, it is also helpful to keep in mind some of the factors which destabilize free radicals, and there are several important trends to keep in mind. Free radicals decrease in stability as the percentage of s character in the orbital increases. That is, as the half empty orbital becomes closer to the nucleus, and for that reason the free radical stability decreases as the atom goes from sp3 decreasing to sp2 to sp. So, as you can notice here, this radical where the carbon is sp3 hybridized is most stable, followed by this carbon where it is in sp2 hybridization, and followed by this carbon where the carbon is in sp hybridization is the least stable. Across a row of the periodic table, free radicals decrease in stability as the electron negativity increases. So, this trend you can see here, out of the free radicals where the atoms are changing in the same row of the periodic table, like you have C dot, N dot, O dot and F dot, the C dot will be most stable, followed by N dot and then O dot and the F dots. Free radicals increase in stability going down a column of the periodic table. So, out of the F dot, Cl dot, Br dot and I dot, the I dot will be most stable, that is the iodine free radical is most stable, followed by bromine free radical, followed by chlorine free radical and followed by the fluorine free radical. And this is because since the electron deficient orbital is spread out over a greater volume. Free radicals adjacent to an electron withdrawing groups are less stable, since in effect electron density is being taken away from what is already there in the electron deficient species. So, you can say electron withdrawing groups will decrease the stability and electron donating group will increase the stability. But if there is a resonance, you have to keep in mind the resonance will be more dominating effect. We can have a handy shortcut for determining the radical stability. We can say, as you can see in this visual, the radical stability increases in the order of methyl is least stable, then primary, then secondary, then tertiary, and this can be attributed to the energy required for homolytic bond cleavage for the corresponding parent alkanes, you can say. So, this is the trend as you can see here, and this is also reflected in the strengths of allylic CH bond, which are weaker than normal due to the fact that a resonance stabilized free radical is produced. So, allyl free radical will be more stable out of these primary, secondary, tertiary, allyl and benzyl. Let us now study the effect of solvents on reactivity of free radicals. The capability of the reaction media to influence the course or rate of free radical reactions has not been realized until recently. The failure to acknowledge the possible importance of the solvent in these reactions rests on the fact that free radical intermediates do not usually have any positive or negative charge and therefore should not be affected by such properties as the ionizing power of the solvent. There are cases where the solvent does appear to have only an insignificant effect on rate, and in a number of cases where there is a small variation in rate with change in solvent, relatively large but compensating changes in the entropy and enthalpy of activation have been reported. However, these later effects have been seriously questioned and they appear to be more a consequence of experimental error than actual phenomena. One of the earliest indications that radical reactions could exhibit a polar nature was found in a study of copolymerization of vinyl compounds. To explain the great tendency for alternation of the two monomer units in the polymer structure, it has been necessary to assume a polar transition state. If there were a highly polar transition state in these reactions, the solvent should be able to contribute to the stability of the transition state in accord with the polar nature. Thus, a pronounced dependence on the reactivity of monomer on the dielectric constant of the solution would be expected. However, experimentation did not show such a dependence. Apparently, the nature of the transition state is such that the lines of force between the charged portions too of the transition state do not radiate appreciably into the solvent. Therefore, the solvent can contribute little in stabilization of the charges in the transition state. Other properties besides the ionization power of the solvent can be important in influencing the radical reactions. The photolysis of aromatic disulfides, for example, shows a solvent dependence between the apparent rate of dissociation and the kinematic viscosity of the solvent. The apparent dissociation appears to depend on the ability of radical fragments to diffuse apart as the viscosity increases and the rate of diffusion decreases, more recombination and thus less apparent dissociation occurs. After the effects of solvents, let us look at the types of free radicals, especially deal with the stable and persistent free radicals first. Although radicals are generally short-lived due to their reactivity, there are many long-lived radicals as well, and these are categorized as stable and persistent radicals. Let us try to know what are stable radicals. Stable radicals, as the name depicts, they are stable and comparatively long-lived. The prime examples of a stable radical is the molecular dioxygen. Another common example is the nitric oxide. Organic radicals can be long-lived if they occur in a conjugated pi system. For example, if you look at the case of alpha tocopherol, which is vitamin E, you can see that the radical here derived from alpha tocopherol can be stabilized via this long conjugation, and that is why this is quite stable. There are hundreds of examples of thiazyl radicals which show low reactivity and remarkable thermodynamic stability with only a very limited extent of pi resonance stabilization. After the stable radicals, let us know what are persistent radicals. Persistent radicals are those whose longevity is due to the steric crowding around the radical center, which makes it physically difficult for the radical to react with another molecule. So, that is the reason why it is the stability is achieved, and these are called as the persistent radicals. Examples of these include Gomber's triphenyl methyl radical, nitroxides such as tempo. Let us study these in detail. But let me tell you here, the persistent radicals, they are generated in large quantities during combustion and are claimed to be responsible for the oxidative stress resulting in the cardiopulmonary disease and probably cancer that has been attributed to the exposure to airborne fine particles. So, the examples of persistent free radicals, let us look at them quickly one by one, their structures, and then you can appreciate how the steric hindrance is making the free radical not react further, and comparatively they are long lived. So, the first is the triphenyl methyl radical, as you can see in this structure. The triphenyl methyl radical, because of the 3 bulky phenyl groups, cannot react with other similar species, and obviously it will be a persistent free radical. This can be easily generated by the treatment of triphenyl methyl chloride, which is trityl chloride, with a metal such as silver, and the presence of trityl radical in solution is easily detected by spectroscopic means, which is the electron spin resonance spectroscopy that you will study in detail later, and it has a yellow color. So, you can immediately notice its formation has taken place by the yellow color. It is also quickly oxidized in air to the corresponding peroxide. The persistent, long lived but not readily isolated trityl radical is in equilibrium with its dimer. Although the dimer is the predominant form at room temperature, that is around 98%, the radical is present to the extent of 2% in the equilibrium. The persistent stability of this radical is the result of a combination of effects, including the conjugative stabilization of the radical by benzylic resonance, and you can see that there will be this resonance into 3 phenyl rings, and the profound steric destabilization which would be present in the normally expected dimer. So, in the dimer you will now have 6 phenyls which will be joined via these 2 carbons. So, that is quite destability. In fact, the actual dimer present turns out to be one in which the aromaticity of one of the benzene rings is disrupted, so that the dimer is destabilized not much by steric effects, but by the loss of aromaticity. This dimer is formed by the coupling of one trityl radical from its benzylic carbon to the para position of the other trityl radical, as you can see here. As might be expected, the tris 4-methyl phenyl methyl radical, which has a methyl substituent at the para position of each phenyl ring, is a persistent radical in which dimer formation is almost undetectable. So, this is the structure of this persistent radical, you can see. Destability of dimer due to destability of the newly formed CC bond, you can say. Not only can a dimer be destabilized by steric interactions, it can also be destabilized by even more fundamental way, that is the circumstance that the new covalent bond formed in this dimer is of a type that is inherently relatively unstable. After this, let us take the case of tempo radical. Tempo radical, which is the abbreviation for 2266 tetramethyl piperidinoxyl radical, and the structure you can see here. This radical exhibits an interest blend of effects which either stabilize the radical or destabilize the dimer. Here dimer formation would require the formation of an unstable OO bond. In addition, the dimer would have steric destabilization from the interaction of the 4 methyl groups on each monomer unit. Further, the radical is substantially stabilized by 3 electron bonding. So, this you can see here is the structure of the tempo radical, and because of the positioning of this radical, the steric hindrance you can see it cannot give you a dimer formation. Another example let us study is the phenylenyl radical. This persistent radical is the, and you can see the structure of this persistent radical. This is highly resonance stabilized radical which proves to be quite stable or persistent in solution, and this again you can notice the free radical pair present at the central location, and you have these surrounded 3 cyclohexadienyl rings which will be providing the resonance stability as well as steric hindrance, so that the dimer formation is a difficulty. So, dear students, let us summarize what we have learnt in this module. We have learnt about what are free radicals and what is their structure. We have studied that free radical intermediates are the chemical species which have a single unpaired electron. And we also studied that the carbon of these free radicals is sp2 hybridized, where the substituted groups may be hydrogen that we have studied, or any other case that is a coplanar structure, that is a trigonal planar, and the unpair or the odd electron occupies a 2p orbital of carbon which is perpendicular to the plane of this trigonal planar structure. The ultimate challenge in attaching an isolabile stable free radical or in solution is the coupling of 2 radicals to produce a dimer. So, if we can trap that, we can then bottle them and use for our synthetic purposes. The radical centers we studied are stabilized by the presence of greater number of alkyl groups which will have plus I effect as well as hyperconjugative stabilization. And we studied that a tertiary radical is more stable than secondary, followed by primary, followed by methyl, and furthermore there can be resonance stabilization. That is why benzyl and allyl free radicals are more stable than even these tertiary, secondary, primary. Although radicals are generally short lived due to the reactivity, there are many long lived radicals as well, and we have studied about them as stable and persistent radicals. And we shall be studying more about these free radicals in the subsequent modules.